Okay, so this recording is taking you through the Excel sheet which I've labelled Week 1 Uniform and Critical Flow Basic Calculations. So we'll be calculating the Manning's cube from the Manning's equation for rectangular, trapezoidal and circular channels. We'll do it with Manning's, we'll do it with Chezy, we'll iterate for the normal depth in uniform flow from Manning's and the Chezy equations, and also iterate for the critical depth and look at calculations using the circular channel as well. So you can see this is a very generic sheet which has not got any specific example questions, but you can put your own numbers in and do those calculations yourself for any question you'll come across to do a check. Okay, so just put the numbers in here for this question. It's a wide channel, 26 metres wide, the side slope S, and let's remember what the side slope is. If it's S to 1, so it's the horizontal value and it's 1 in the vertical. The bed slope for this example, we're going to use 0.0001. The Manning's N we're going to use fairly smooth, 0.013, and the normal depth for this example we're going to use 1.4. Okay, so area, we're going to use this formula here, so that's simply a bracket. We copy exactly that formula, 1 equals B plus S times Y bracket times Y again. Weighted perimeter, going to use this formula, so B equals B plus 2 times Y times the square root of 1 plus, and the side slope squared, which we can do it by doing it like that. And R, simply A divided by P. Now we normally just calculate Q when we're calculating the uniform flow, but in this example I'm going to use the V formula first of all. So I'll do that, and I'm going to write it 1 divided by N first in brackets, and then times this by R raised to the power of 2/3. I could have put in there 0.666, but I'm using 2/3, using raised to the power of 2/3, and then it's the bed slope raised to the power of 0.5. 2.97 meters per second, so it's fairly fast. We can simply calculate Q, let's use that, times by the area, 542 meters cubed per second, so pretty massive flow. We can try calculating the formula directly, let's type that in, so we can just do a double check. So again, I'll do the 1 over N first of all, times it by A, times it by R raised to the power of 2/3, times it by the bed slope raised to the power of 0.5. Same. Okay, so a little check there. Okay, let's do a calculation using the a uniform flow, Manning's equation calculation using a circular channel. Well, let's just highlight what we're looking at in a circular channel. So we've been given a diameter and a depth. So if we look on this diagram here, we'll see that the depth is the height from the base to the water surface, and capital D is the diameter. What we do the calculation in terms of a circle is in terms of phi. We'll iterate on phi if we're doing an iteration, but we need to convert things into phi because all our formulas are in phi. Remember that phi is in radians, so we need to convert the depth into this angle that subtends from the centre to where the surface crosses. So we're going to need this at the bottom of this table, conversion from the depth, so it's the second last equation, depth, to give us phi. Or if we've got a phi, we can calculate the depth. Okay, so let's go and look at that calculation. So we're given 0.4 diameter, 0.2 depth. Well, we can see by inspection there that the depth is halfway across, so we're going to expect to be phi to be half a circle, which is pi. But let's use the formula. Bed slope 0.02, Manning's 0.014. I'm going to delete that there. We shouldn't have had that there. Let's use that formula. So let's do this second last formula here. So phi is equal to 2 times, and it's a cos to the minus 1, arc cos, a cos 1 minus 2 times y divided by the diameter, and it comes up 3.142, which we know is pi, and I've actually done a conversion formula there just to check, and the conversion formula is, well, it's not a formula, it's the function degrees, and you put a radians in and it gives you degrees out, so 180, we know that. Right, now area is this first formula, and I'll write it with the brackets first. So phi minus sine of phi, and I'm going to just put that in brackets to be sure. Oh no, I don't need that bracket, let's get rid of that. Times my d squared, the diameter squared, d and that squared, all divided by 8. Now I'm not sure whether it's going to put 2 over 8, but I think that is correct. That's going to use the 2 and divide it by 8. So area, yeah, that is correct. Wetted perimeter, half phi d. So this formula will be phi times d divided by 2. R, this is easy, just A divided by P. The velocity, well, we're just going to use this formula again. I'm going to copy them both down here so they're handy. So the formula for velocity is equal to 1 divided by the Manning's n times by r raised to the 2/3 times by the bed slope raised to the 0.5. Great. Q is just velocity times area. Oh, what's happened there? Oh, that's right. Then let's do this first formula for Q. 1 divided by n times by the area times by r raised to the 2/3 times by the bed slope raised to the 0.5. Okay, check those two numbers are identical. We're okay. Right, we'll now go and do the same calculations with the Chezy Q, and I'll do this very quickly. All we're doing now is applying the equation for in the form of Chezy. So far, these three, no, I could copy them over, but I'm not going to. I'm going to put them in properly. A is equal to B plus side slope S times the depth times the depth. Yep, just look at mistake. There should be S. P is equal to B plus 2 times depth times the square root of 1 plus side slope squared. 134. Yep. A R is equal to A divided by P. Velocity, we'll put in that formula. It's a bit simpler formula than the Manning's because there's no division of the friction, so equals to C times R raised to the half this time, remember, times by S0 bed slope raised to the 0.5. And Q is just velocity times area, 268 in this example. We can use the first formula. It's equals to area times Chezy C times R to the 0.5 times S0 to the 0.5. Again, that's about right. Same value. We're going to do the same calculation again using the Chezy equation for the circular channel. And I'm just going to copy the formulas down here. So they're nice and convenient. Right, A is equal to, okay, so I should just say I've done the calculation for phi as applying this first equation, sorry, this second equation in here to A cos 1 minus 2 times y divided by d. A is equal to, well, I just need to remind myself of these formulas now. I've got them on my previous sheet, so let me copy them here so they're handily available to me. So A is equal to bracket phi minus sine and open bracket phi close bracket time, oh, I need a bracket there, times d squared divided by 8. B equals phi times, oh, equals phi times the diameter divided by 2. R is equal to A over P, as always. Okay, I did a mistake there. Chose the wrong one, let's just correct it. V, we'll just apply that formula, is equal to C times R to the 0.5 times S0 to the 0.5, 1.79 meters per second. Q is just the velocity times the area. Or we can apply the formula is equal to the area times C times R to 0.5 times slope raised to 0.5. Okay. Alright, we can do iteration of the Manning's equation. I think I'm going to stop before we get too long.